welcome back to Advanced Organic 3120. JP here. Today we're going to finalize our discussion on the Aldol reaction, and we're going to specifically focus on the stereochemistry of the Aldol reaction. So this is actually located in chapter 33 of your textbook in case you would like a reference. But anyways, let's get started. Okay, so by now you are an expert on the Aldol reaction, and you should be very comfortable in performing and doing the Aldol reaction and understanding the mechanism. So if we look at this reaction here, if we treat this ketone with LDA, you know you'll generate a lithium enolate. And then if we treat this with an aldehyde, so this would be a directed aldol approach. You know that this will react, this will come down. This electro or nucleophilic carbon will come and attack the aldehyde. So you can generate the product, and let's draw the non-dehydrated product, so the hydrated product. All right, so there's your aldol product. Now the question I have for you is, during this reaction, what are the new stereocenters that are generated? Right, we've gone from molecules that do not necessarily have specific sp3 stereocenters, but during this reaction, we actually have two new stereocenters, and they are actually here and there. So the question now is, well, what is or what occurs stereochemically during this reaction? So let's take a look. So in reality, when you actually perform this reaction, we do this with LDA. Again, just emphasizing that we keep this at cold temperatures because we are dealing with lithium enolate made by ketone. And if we do this reaction, we actually generate two different stereo products. We generate this product, which is known as the Syn Aldol product, because both of these groups are on the same side. So it's like a syn addition. Plus, we generate the other stereoisomer, where you have both of these groups on the opposite side. So we call this the Anti-Aldol product. And doing this reaction, we really can't tell which one will be the major product or not. But there must be a way for us to do that. So let's take a closer look. So it turns out that a lot of this is influenced by what the geometry of the enolate is. And we haven't really considered that, but let's take a closer look. So if we start with our lithium enolate, and the enolate can exist in two main forms. They can exist in a cis and a trans form. So here I'm showing you the enolate in the cis conformation, because you can see that this group here is on the same side as this methyl group, or in this case, this would correspond to a trans enolate. So if you take, for example, a cis enolate and react that with your electrophilic aldehyde, the major product that you will get is the syn addition product. In contrast, if you do this with a trans enolate, we'll keep our substrate the same. You will generate the anti-aldol product. Hold on a second, I just made a little error here, so this should be pointing towards you, right? This is the syn products, or they're both the same. Whereas if you use a trans enolate, you're going to generate the anti-aldol product. Okay, so that's interesting. The geometry of the enolate greatly influences the stereochemical outcome of this reaction. So if we look at an example where we could say, well, where we could fix that enolate, because in reality, if we do this reaction with the substrate up here, you could imagine this could exist in both cis and trans enolate forms, and very likely that is what is going to happen in solution. So let's look at a couple different examples where we know for sure if we have a trans and cis enolate. If we take cyclohexanone and treat this with LDA, what kind of enolate will we make? Well, we have a 6-membered ring, so the only way that this enolate can form is through the trans orientation. So this is a trans enolate, and if we react this with a substrate, this will react together, and we are therefore going to generate the anti-aldol product. Okay, so this will come down. This is going to be your new carbon-carbon bond. And specifically, because this is anti, therefore this carbon here is going to come towards you. You can imagine you have a hydrogen going away from you. And I'll just draw on the other hydrogen here, showing that it's coming towards you. So this is the anti-aldol product. And let's think of a scenario where we would have exclusively a cis enolate. And the best example I can give you is if we have a bulky group on the R side of a ketone, and if you think of two different enolates, it would be better to form the cis enolate from this ketone, because this group here is now cis, and there's no steric clash with this carbutyl group. If it were trans, then you'll start to see some steric clash, and that would be not favorable. Okay, so this is a cis enolate. This is trans up here. So when this reacts with the electrophilic substrate, we are going to get a Syn Aldol product. as our major product. Okay, so those are some examples of how we can predict the stereochemical outcome. But you guys are just taking my word for this, and let's take a closer look, at the atom-to-atom connectivity, so we understand why trans-enolate leads to anti-products, anti-aldol products, and why cis enolates lead to Syn Aldol products. Before we do that, let's do a little review on the chair structures of dye-substituted cyclohexane derivatives. So this is stuff you have seen from second year organic chemistry, but I think it's good to review it. And specifically, we're going to use what we learned from this, or what we've reviewed, and apply it to the aldol reaction. Dye-substituted cyclohexane derivatives. All right, so let's take a look first at 1,4 dye-substituted derivatives. If you have a cyclohexane ring and you have two substituents, we'll just call them X, coming towards you in this environment here, what does that look like in terms of its chair structure? Okay, so here's one chair. When they are like this, what this means is that you have one group that's axial, one group that's equatorial. Okay, so here's a group that's equatorial, then 1, 2, 3, 3 carbons over. You have a group here that's axial. This ring can flip, and it can flip, and essentially when it flips, you're going to get this substituent at this position and this one down here. So when we flip the ring, you're now going to change this to axial, and then this one here is going to be equatorial. Okay, so that's what for 1,4 disubstituted. If we take our 1,4 disubstituted and we put an X group at the top that is now away and this one towards us, the chair structures are going to look like this. You're going to have a situation where you have two groups that are now in the axial position, and then if this flips, now these two groups are going to be equatorial. Okay, so you've seen this in second year organic chemistry. If we look at the relative distribution of these chairs, you can see here that we have one equatorial, one axial. When we flip it, we have one axial, one equatorial. So the energy between both of these are equivalent. So you're going to get an equal distribution. On the other hand, in these chair structures here, you have two axial, two equatorial. So the equatorials are, of course, a lot better. So in terms of equilibrium, this one's going to be heavily favored and just a little bit going that way. All right, so that's 1,4 derivatives. Let's take a look at 1,3 derivatives. Okay, so 1,3, you're going to have two groups. One of them, you're going to have these two X groups that are axial. You can see you're now generating a lot of 1,3 diaxial interactions, which is not favorable. However, if you flip that chair, you are now going to put those groups in the equatorial position, which makes it much more favorable. So the equilibrium will lie heavily on this side, just a little bit on that side. And just to be complete, if we draw this other 1,3 disubstituted derivative, and we draw the chair conformation, you can see here that you now have, this remains axial, but now this one here is going to be equatorial. And then if you flip this chair, you'll now go from axial to equatorial, equatorial to axial. And the relative distribution for both of those are going to be the same because the energy for both of those are the same. Now, lastly, we got to look at 1,2 derivatives, and this is going to be very specific for what we're going to be talking about with respect to the Aldol reaction. So let me just erase this board here. I just have to remember where I put my eraser. Here it is. Two disubstituted derivatives. All right, so we would have something like this, and then you would also have both of them like that. So two different derivatives in terms of what their chair structures will look like. They're adjacent to each other. If they're like this, what it means is that you have one axial, one equatorial. So that's one structure. And if this flips, you're going to have your axial flipping to equatorial and equatorial flipping to axial. Relative distribution for both of these are the same. In contrast, when you have them oriented in this orientation, you're now going to have equatorial, equatorial, and if you draw the other chair, you're going to flip both of those equatorials to axials, and you already know that's less favorable. So that's going to look like that. Okay, so this is your review on chair structures, and as I mentioned, we're going to be looking at 1,2 derivatives specifically. This is going to guide us for understanding the stereochemistry of the Aldol reaction. So make sure you really understand all of them, but at least the 1,2 derivatives. All right, so let's take a look at the chair transition state using a Cis Enolate. So here is your Cis Enolate, and it's going to react with an aldehyde, and the aldehyde, let's just call the aldehyde like this, and we're going to draw the transition state of this reaction during that aldol reaction, and it's going to orient itself in a specific 6-membered ring orientation, as you might imagine, based on some of the structures that I've drawn. So I'm going to show you what this looks like. And at the beginning, it might seem a little, might be a little hard to see. So, bear with me and take your time drawing it. And you might have to draw it a few times in order to see that chair structure. Okay, so here's a Cis Enolate. I'm going to draw this in a slightly different way. I'm just going to make sure you put R prime here so we can distinguish that from R. Okay, so I'm drawing the Cis Enolate in a slightly different way, but it's the same compound. You can see the oxygen and this group here, they're on the same side. And it's a lithium enolate, so what you're going to do is you're going to have good tight interaction with that lithium cation, which I'll put right there. Now we're going to get this to react with the aldehyde. And you can imagine during this reaction, this will come down. This is your nucleophilic carbon. So the electrophile, let's position the electrophile right at this position here. Okay, so our electrophile is our aldehyde. And it's going to also have some type of interaction with that lithium. And then at this stage here, we are now going to decide which way to put the aldehyde in. We have an R group on one side, and we have a hydrogen on the other side. So now I hope you can see that we have something that looks, or starting to look like a chair structure. And in fact, I can clean this up just a little bit to make it look even better. Right, there's the chair structure, right? Okay. So when I'm placing the R group and the H group, if we can imagine a chair structure, we have a couple of choices here. We can put a group here like this in the equatorial position, or we can put a group here in the axial position. What would be more favorable? Putting the R group in the equatorial position or the axial position? Since the R group is going to be much bigger, it's going to be much more favorable to put that in the equatorial position and put that small hydrogen in the equatorial position. Okay, so now what you can see is that this is going to come together and it's going to react in this three-dimensional format in a chair-like position. So we actually call, so when this reacts, let's draw what this looks like, and we're going to keep the same orientation, and we're going to keep it looking like a chair as much as possible. Okay, so that's the new carbon-carbon bond that you made. And you can see here I've done my best to keep that same chair framework, right? So draw the chair out so you can see the backbone of it behind it. But what's important here is this new carbon-carbon bond. And what I've done is I've drawn these groups in the same orientation. So you can see here that this corresponds to a group that would be axial. So we call this actually pseudo-axial. And we call this group pseudo-equatorial. Now, so when you quench this reaction, when you add water, you're not going to have this oxygen lithium. So we're just going to throw on a proton, and it's going to look, it's going to look the same. Okay, but again, this is your pseudo-equatorial group, and this is your pseudo-axial group. Now, how do we go from a structure that looks like this, where we've labeled them pseudo-equatorial, pseudo-axial, to the Syn Aldol product, which we know happens with Cis Enolates? So let's take a closer look. I'm going to use the blackboard, so take your time. I know sometimes during the day there's a bit of glare from the back windows, and I think the contrast, especially for these structures, will be better when I draw them on the chalkboard. So just bear with me. Okay, so let's think back to our 1,2 disubstituted derivatives. If we had something like an R group or methyl group that was equatorial axial, we know what that would look like, right? We know that they would actually correspond to something where they are both on the same side with respect to, you know, a cyclohexane derivative. Okay, so it would look something like this. So how can we draw this in such a way, and we're just focusing now on this portion here to account for those groups being on the same side. So let's draw this in this format here. And what I'm going to do is I'm going to put, again, our methyl group right here on this side coming towards us. I'm just going to draw the hydrogen here, and then here I'm going to draw this R group, right, which would be coming towards us, and then you'll have this hydrogen going away, and then you'll have this OH group. So you can imagine this is looking like this area here is corresponding to this portion of the ring, which we know exactly based on the rules of organic chemistry. Okay, so this corresponds exactly to that product. Now when we draw aldol products, or typically organic compounds in general, we always put the carbon chain in the plane of the page, the longest carbon chain in the plane of the page. So you can see here, this is your carbons, this is in the plane of the page, and then this is all in the plane of the page, but now you have this R group coming towards us and the hydroxide group in the plane of the page. So what we need to do is rotate this group so the R group is in the plane of the page. So how are we going to rotate that? So we're going to take this bond here, and imagine if you're looking at it this way, and we're going to rotate this just 60 degrees in this orientation. If we do that, then this R group that's coming out towards you a little bit will now go in the plane of the page, and then this hydroxide group will come out towards you a little bit, and the proton will still, or the proton or the hydrogen will still remain behind you. So if you rotate 60 degrees, this is going to look like and just so I'm consistent, well, it's funny, at the beginning I put R primes for that Cis Enolate, and then I forgot them all. So why don't we start back here, put these R primes in, because we're differentiating it from this R group. R prime, R prime, R prime, R prime. Okay, so this is your product, as I'm showing you here. And this is your Syn Aldol product. What you will learn is that if you see one group that is in the equatorial, and then this R group in the pseudoaxial position, you can immediately go and put the CH3 group, this R group on that side, and the hydroxyl group on the same side. Okay, but I want to go through how we got there using that three-dimensional model. So this is how we get to the Syn Aldol product. All right, so let that digest for a little bit. Let me write a note here too, saying that an axial, and I put axial because we're really talking about not a true chair, but a pseudo-axial position. An axial and equatorial adjacent to one another corresponds to a cis 1,2 a cis 1,2 disubstituted cyclohexane species which also corresponds to with respect to what we're talking about, a Syn Aldol product. This six-member transition ring is called the Zimmerman-Traxler transition state. Okay, so let that digest for just a moment. I'm not going far. All right, good stuff. So let's look at the situation where you have let's look at the chair transition state of a trans-enolate and see what that looks like and how that will give us the anti-aldol product. So again, what I'll do is I'll erase this because I'd rather use the chalkboard. Okay, so chair transition state with a trans-enolate. All right, so let's use the same type of substrate. So this time we'll make sure we keep that R prime. In this case, because it's trans, we're going to put that methyl group here, and then the hydrogen will be down there. And this is O minus. That's going to be coordinated to the lithium. So the lithium plays a really important role because it really serves as a bridge in that six-membered ring structure. We're going to have our aldehyde, and again, we're going to put that R group in the equatorial position because it's much bigger than the hydrogen. Okay, so when this comes and reacts, going to react like this. Here you have methyl, hydrogen, R group, okay, so it's going to look like this. When you quench that with water, it's going to look like that. And you can see here that you have your methyl group here. This is in the pseudo equatorial position. In addition to this R group is also pseudo equatorial. Okay, so how do we go from this to that final anti-product? And again, keep in mind that we are looking at two groups that are equatorial to one another. So they're going to correspond to a trans disubstituted species. And again, we're going to be kind of focusing on this area here to help us draw what that aldol product will look like. All right, so let's start drawing it. So this is equatorial, so this group is going to come down like this. CH3 group, hydrogen will be going away. Let me find a bigger piece of chalk. And then as we move our bonds to this one here, the R group has to be placed away, and the hydrogen is going to be towards us. Don't forget your prime here. And then this is OH. And then like I've mentioned before, we got to put the longest carbon chain in the plane of the page. And so what we need to do is we need to imagine our eye going this way, and this is coming away, but we want to put that on the plane of the page. So we need to rotate it now this way, and we're going to rotate it 60 degrees. So now this R group is coming down this way in the plane of the page. So what that will look like is this. So it's the same structure, right? It's just drawn in a way that is used conventionally for organic compounds. So now the longest carbon chains in the plane of the page, you can see that your methyl group and the hydroxyl group are anti to each other. Yeah. And just to make this complete, just recall that this here corresponds to this chair structure where you have X equatorial, Y equatorial. Okay, so again, that corresponds to this, this corresponds to these exact positions there. So that's how we're doing the stereochemistry. So that's pretty cool, right? You can definitely predict exactly what the stereochemistry will be during this reaction. So let's go through, let's go through one example and then we'll finish, and then that'll be the end of this lecture. All right, predict the product major plus minor. All right, so the question is, if we treat this cyclopentanone with LDA, second step acetaldehyde, and then 3 water workup quench, what is the major product going to look like? Major and minor. Turns out there are 2 products. And use 3D models, to show using that Zimmerman-Traxler transition state. So this is a 5-membered ring. The only type of enolate this can form is a trans-enolate. So that's completely fixed. So let's draw what that trans-enolate will look like. Okay, so I'm starting it off exactly like I've done up there. The difference is that it's a 5-membered ring. So you can see that all this stuff is on the trans side of the oxygen of the lithium enolate. This will coordinate to your oxygens of the acetaldehyde. We'll put the R group like I'm showing you here. And then as you can see, when this comes down and reacts, we are going to generate a structure that looks like this. Okay, so that's your chair-like structure when that quenches. This looks like this, your Zimmerman-Traxler transition state. Okay, you have your R group here, which is equatorial. And you have this group, which is part of the ring, but it's the trans-enolate. This is also equatorial. So they're both equatorial. So when you draw out what that product's going to look like and putting the longest carbon chain in the plane of the page, you're going to draw these 2 groups anti to each other. Okay, so your major product is going to look like this. But the question is, you're going to get a minor product too. Predict the products, major and minor. That accounts for this. What do you think the minor product will be? And you might say, well, maybe we could take that trans-enolate and flip it to a cis. But the thing is that we can't do that because the trans-enolate is the only one that can form from that 5-membered ring. So what other options do we have? So the only other option is at this stage here. With the aldehyde that we've put in, we've placed it in the lowest energy, more stable conformation, but what if we flip it and put the R group axial and the hydrogen equatorial? If we do that, it's higher energy, but if it reacts, what is that going to look like? So let's take a look. Yeah, so we'll put this hydrogen equatorial, put the R group axial. Reaction happens. Let's see what this looks like. There's a new carbon-carbon bond. This R group is axial. Okay, so this is with, after it reacts with the quench, carbon-carbon bond. So you can see here that this is pseudo-equatorial. This group is here is now axial. So you have a situation where you have one group equatorial, one group axial. This corresponds to a cis 1,2 disubstituted cyclohexane derivative, which in our case corresponds to the Syn Aldol product. So that's going to look like this group coming towards you, and then the hydroxide group coming towards you, like this. So this will be your minor product. I don't know what the relative yields are. Really, that would depend on the R group, but you could imagine that a bigger, more bulky R group would be more inclined to generate the anti as a major product, whereas if this were much bigger, then the Syn minor product would be much, much smaller. All right, so I hope you enjoyed this lecture on Zimmerman-Traxler transition states. Definitely a lot of different types of mind thinking here to account for the stereochemistry. So definitely take your time with it. And again, if you have any questions whatsoever, you're always welcome to contact me or the TA, and we'll discuss this, at course packs. And I look forward to those discussions. So that's it for today. See you next time.